In chapter 15, we're going to take a look at a non-parametric method for analyzing nominal level of measurement. If you recall, a nominal level of measurement is one that the measured outcomes are labels and there are no numerical values to them. So these are often called qualitative or categorical variables. So we haven't really analyzed any categorical variables. This is the first time we're doing it. The procedure we're going to use, the test we're going to use, is commonly called a ChiSquare test of hypothesis. Okay, so in order to do this, we're going to look at a contingency table. That's the scope of what we're covering there. This test is also intended for other purposes, but we're only going to look at it in the way of testing association between two nominal or categorical variables. Okay, so here I have is a contingency table. So what is a contingency table? A contingency table is simply the frequency distribution of bivariate data. Now when we say bivariate data, the prefix bi meaning two. So we have two variables, and keep in mind both of these variables are nominal. Okay, and just like with any table that we create, there are rows and columns. So the row variable is whatever that variable, first variable is, and the column variable makes up the second nominal variable. Each row makes up levels of variable 1, and each column makes up levels of variable 2. We'll see two examples in a few moments here, and that will clarify this for us. So what are we interested in? We actually want to determine whether there is an association between the row and column variables. It's very simple. That's all we want to do. Now, some people think about the association in terms of independence or dependence between the variables, but you got to be careful with that, because when we talk about independence or dependence, especially in the case of dependence, we do not want to confuse dependence with causation. So in other words, we're not going to say that variable 1 is causing variable 2 to change, or the outcomes of variable 2, and neither is variable 2 causing the values or outcomes of variable 1 to occur. So we're simply looking at association. Is there an association between these two? A statistical association, that is. So again, the procedure we use is called a chi-square. Notice this is, I know it looks like chi, the CHI, but it's pronounced as chi. And more specifically, this is what we call a Pearson chi-square test of independence. This the chi-square probability distribution actually was discovered by Professor Carl Pearson in the early 1900s, and also a German statistician by the name of Hermert at the same time pretty much discovered this probability distribution. So in Germany and Europe, they know this as Hermertian test of independence. But anyhow, we're going to call it a Pearson chi-square independence test. So again, the word chi-square is motivated by the chi-squared probability distribution. Now, since we're using software, Megastat, we're not going to look at the details of a chi-squared probability distribution and nor the formulas. We're just going to be able to interpret the output. So, when we're doing a Pearson chi-square test for independence, what are we looking at? Well, we're looking at these two hypotheses right in here. That's what we want to do. We want to test these two hypotheses. The null hypothesis here reads, the two variables are not associated. In other words, they're independent. The two are independent. The alternative hypothesis, on the other hand, takes the other side of that and calls for dependence or association between two variables. And that is what we're hoping for. Like when you do a research, you're hoping to show that there is some kind of association between variables. Because remember, null is always the status quo. Null says there is no association between any two variables in the world. So we want to actually refute or reject that hypothesis. Okay. The other point I want to make out is that every contingency table is made up of cells. Okay, so what is a cell? A cell is simply a row-column combination where a row and column meet. They create a cell. So we'll see this in a moment in a table. Now, these are the assumptions that go with the ChiSquare statistic and with the ChiSquare test for independence. All expected cell frequencies are 1 or greater, and at most 20% of expected frequencies are less than 5. And of course we have a simple random sample. I will explain these in context of an example that's coming up in just a moment, and once we have the output, I'll come back to these assumptions and show that these assumptions are met. So let's take a look at our first example here. Okay, and it's an interesting example at that. So here we have it. In this example, let me enlarge the font here. Okay, let's take a look at the example now. In this example, the question reads, at an umbrella manufacturing facility, umbrella handles are measured and then removed from the assembly line if they don't meet specs. A daily report indicates how many rejected handles were produced by each of 3 presses. These are press machines at the facility during each of 3 shifts. So we got 3 machines and there are 3 production shifts. A quality engineer wants to determine whether press and shift are associated. So are there any dependencies? Is there anything, in other words, going on with the machines and then during different shifts as it relates to these handles that are actually rejected, right? These are rejected products, so these are not good products. So the engineer performs a ChiSquare test for association to determine whether the press and the shift that produced the rejected handles are associated. Again, these numbers are numbers of rejected umbrella handles during each shift produced by each machine. So this is all bad stuff. Okay, we're going to of course use your usual 0.5 level of significance. So here's the null hypothesis. Remember, the null hypothesis is always, in this case, the hypothesis of no association between 2 variables. That would imply independence. Statistical independence, that is. So that's what we're going to write, that there is no association between the row variable here is machine. There you go, each row, row 1, row 2, row 3, that constitutes machine 1, machine 2, machine 3. And the column variable here is shift. And these are the levels of the column variable. Column 1, column 2, column 3, so that means first, second, third shift. Okay. And there is our contingency table. So this is a 3x3 contingency table. Now the row column combination for any one of these, for example, second row, third column, these are the number of rejected handles that are produced by machine 2 during the third shift. You see that? 32. That's a cell. So we got cell, 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 and so on. Okay, so there you go. Now let me show you the output from Megastat, and then we'll go and produce these outputs so we can maintain continuity with what we're doing, so we don't get sidetracked with just jump into Megastat here. So, but I'll show you Megastat in a moment. So this is the output that actually you're going to be getting from Megastat. Pretty elaborate. Now, of course, Megastat doesn't quite produce it in this form. Remember, once the output comes in Megastat, it belongs to Excel. And you can highlight it, you can boldface it, you can do whatever you want with that table, and that's what I've done. And then I copy and pasted it into my note. Okay. So here's the title: ChiSquare Contingency Table Test for Independence. That's what Megastat calls it. Now, remember we had 3 machines, machine 1, 2, 3, and we had 3 shifts. Now, everything that's in boldface, bold, 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 these are actually the observed frequencies, right? So if you go back, for example, machine 1, shift 1, 48 observed, and there you go, 48. Machine 3, shift 3 had 34 rejected handles. Machine 3, shift 3, 34. It's machine 3, shift 3, and 34. So you see the boldface numbers? These are all observed. These are observed frequencies. Now, and then we formulate, or Megastat calculates the expected frequencies. The expected frequencies are what you would actually expect to see. This is how many rejected handles you would expect to see if the assumption of independence was true. If there was no association between machine and shift, this is what you would expect to see. Now, the formula that gives you these numbers, we're going to skip over those formulas. Okay? So, for example, check out this number 40. During shift 2, machine 3, 40 rejected handles were observed. These are the actual observed frequencies. The theory says you should have expected 36 of those had the assumption of independence been true. So Megastat gives you all of these expected, and then the marginal totals, I have them in green. So here, 143. In other words, the total during 3 shifts, total rejected handles from machine 1 were 143. Machine 2, 155, and machine 3 is 110. Total number of rejected handles during shift 1 produced by all machines. The total, 160, 134, 140. The grand total produced during 3 shifts coming out of all machines. This may be 1 day production. 408 rejected handles, umbrella handles. So the things that you see in here, actually I have on the body of the table, and this particular one's in the margin. So for example, if you look at shift 1, the greatest number of rejected handles come during shift 1. So shift 1, look at comparison. Shift 1, shift 3 is doing better. In fact, it's the best shift of all 3 shifts. In terms of number of rejected handles, it has the lowest number of rejected handles. Now, as far as the machine goes, machine 1, 143, machine 2, 155. Machine 3 is doing the best job, producing the lowest number of rejected handles. Okay. Now, if you focus more closely here, for example, here I have during shift 1 out of machine 2, 76 rejected handles. That's out of 155. So almost half of those rejected handles come during shift 1 out of machine 2. Now here's what you need to actually look for on this table. These percentage. So you have, remember this, look at this row, percent of chi-square, percent of chi-square, percent of chi-square. What we typically look in this table, because you got a whole bunch of numbers here, right? What you really look for is the percentages here, the ones that have the highest percentages in the table. I got a percent here, a percent here, percent. There's going to be a percent for every cell, every row column combination. Now, looking at the greatest percentage here is 32.3%. Now, what is this percent of chi-square? 32.3% of the overall chi-square statistic that was calculated is due to machine 2 during shift 1. The next highest is 25.1% coming out of machine 2 during shift 3. So it looks like clearly machine 2 is having some kind of issues, right? See, the greatest number. And in fact, if you look at of all of these total 408 total rejected handles, 60% almost come out of machine 2. So machine 2's got some issues. Okay, now apart from machine 2, looks like shift 1 also. We need to take a look at shift 1. Next to that, look at shift 3. Shift 2 looks fine. Now look at this one, the 0%. During second shift out of machine 1, 47 faulty handles were observed. The theory says if the shift and machines were independent, you should expect about 47. So this is fine. There's no issue with the shift 2 out of machine 1. So see that 0% contribution to the overall chi-square statistic. So that's what these percentages are. These are contribution to the total chi-square test statistic. Okay, and then of course, this is the value of chi-square. This is like your z-score, your t-score that you get. Okay, your test statistic. We've seen those before. This is a chi-square statistic. Again, all you need to worry about is the p-value. If p-value is small, we're going to reject the null. So remember, p-value here is 0.019, and the alpha level, significance level, was 0.05. So putting it all together, this is what I have. So pretty much I wrote down what I mentioned earlier. So it looks like PERS 2 during shift 1. The engineer need to investigate that and see what's going on with that machine during shift 1. Then I would also recommend that look at machine 2 during shift 3. It looks like machine 2's got some kind of issue. Okay, aside from everything else. Aside from, the shift during the shifts. So maybe the operators have something to do with this. That's why they need to be investigated. So as far as our decision here, because p-value is less than 0.01, less than 0.05, we're going to reject the null. So that means if you reject the null, we're going to go with the alternative. Remember, the alternative says there is an association between machine and shift. So it needs to be investigated. Now with that, let's go to Megastat and actually create this table. You see how easy it is. Easy it is to do this. Okay, so I am in Excel and I have a Megastat as in my add-ins. So here's the data, the way you want to input the data actually in order to do the contingency table. Make sure you have shift 1, 2, 3. In other words, you need to write the levels of the variables, column variable. You need to have every level of the row variable and then the frequencies. That's it. You just do that. And check out how easy it is to do this. You go to add-ins. And then you go Megastat. Go down to chi-square cross-tabulation. Cross-tab. Now, it gives you 3 options to the right. Goodness of fit, cross-tabs, contingency table. Just the easiest way to do this is to do a contingency table. We can actually do the other 2, but then this is the easiest. The other 2 take longer to do, and we gotta do more work. So let's just go to contingency table. See that? Click, and our input range, because I ran it before, let me show you this. Don't worry about the stuff here. My input range is, let me X this out and clear. Okay, hold on, let me clean this up. Okay, that other thing that was showing up is for our next example, so I just moved over to this one. So anyway, there you go. So you got your column, you got your rows, and this is our table. So again, you go to add-ins, and then we go to Megastat, we go to chi-square cross-tabulation, and click on contingency table. And this is the pop-up. Now the input range. Now if you read below it, it reads input range may include row and column headings, but do not select totals. Remember those marginal totals that I showed you? They were not even in the example that I made up. So let's go to input range and look how you're going to select. You go from blank corner, you left click once and hold. Okay, left click and hold on your mouse. And let go of the mouse. There you go. You see how I have selected that? This will outline my range of data values. So although that cell is blank, you want to include it and then hit enter. Now down here you get a whole bunch of stuff you can choose. The things that I'm interested in is the chi-square value, expected values, and percentage of chi-square. Now before I click, see I'm holding the mouse over that spot, and below it reads percent contribution to chi-square for each cell. This is actually very interesting. And these are, by the way, to the side, these are some of the other non-parametric methods for association, but we will not discuss them. Hit OK. And there you go. This is what I had. So these are now familiar numbers. And again, once this is output into this Excel, Excel owns it. Now Megastat is out. It's done. So anything you do in your spreadsheets in Excel, you can do it with this output. So you can highlight it, boldface it, change the column width. There you go. See, I'm changing the column widths. So Megastat is out. We're just now dealing with Excel. And there it is. We already went over the table, and p-value is 0.019. Megastat actually paints it in a different color when it's significant, below 5% by default. So we're going to reject the null hypothesis, and this is where I got that Megastat output from. Okay, so I'm going to pause and I'm going to go back to my note. Okay, we're back in my note. Now let's take a look at another example. In the second example, the question reads, is someone using a cell phone more likely to be involved in an accident? Use the following sample information to answer the question at alpha 05. Our significance level is 05. Okay, so here's your contingency table again. So we got a 2x2 table, 2 rows, 2 columns. So the column variable is the status on the accident. So variable is accident. And notice, by the way, how nominal these are. Had accident, did not have accident. Those are nominal outcomes. Use a cell phone, doesn't use cell phone. Those are nominal outcomes. So the row variable is cell phone usage. The column variable is whether it's just accident. Now, and here's the actual observed frequencies: 25, 50, 300, 400. Okay, so just looking at this, we'll bring it down to Megastat output now, right here. So as far as the total goes, the totals are how many people in the sample size is 775. Of these 775, those who use cell phones, 325. 450 did not use cell phone. How many had accident? The total is 75. How many didn't have accident? 700 did not have accident. Okay, now let's say those who had accident and use cell phone, 25 people qualified. Now let's take a look at this one. So remember, going based on what I mentioned earlier, we look for highest percentages in the contingency table. So the highest percentage is this one right in here, 52.4%, right? So I'm gonna highlight that one. Maybe let's use orange, light orange. Okay, and there you go. That's the greatest contributor to the chi-square statistic. The next greatest is this one right in here, 37.9%. There you go. So those who had accidents, majority of those who had accident used cell phone. Okay, right, 52%. Because these totals, these should add up to, let's see, yeah, 30, 80, that's 90%. Okay. Okay, that's, never mind. That's contribution to ChiSquare. Okay, it's not the percentage who had accident. 25 out of 775, that's what percentage who had accident. You can get those percentages, by the way, if you want, in Megastat. I'll show you how to do that. But again, these are percentages that are contribution to total ChiSquare. So if you add 52, 38, 5.6, 4.1, these four percentages add to 100%. Okay, now look at the p-value. Our p-value is large. We're not going to reject this null. Okay, we do not reject the null. What does the null say? Null says that cell phone usage and having accident, there is no association, independent, and we're not going to reject that null. So the null stands. There is no association between cell phone usage and incidence of having accidents. Okay, and the chi-square statistic is pretty low here. Okay, but again, the greatest contributors to this small chi-square are these kind of users. But again, there's not enough evidence to sound the alarm here. For example, say those who use cell phone necessarily have greater rates of accidents. So I'm gonna fail to reject the null. There is no association between cell phone usage and getting into an accident. Okay, so now let's go run this in Megastat. Okay, so I'm gonna pause and go to Excel. Okay, so I'm in Excel now, and here you go. The data again, 2 rows, 2 columns, and these are the observed frequencies. We go to add-ins and click on add-ins, Megastat, and we go to ChiSquare Contingency Table. Our input, erase the previous input, that's new input. I'm gonna actually, there you go, highlight this for my table. Let me show you. There you go. You see what I highlighted? This is for our new example. Enter. And right in here is what I was talking about. See, percent of row, percent of column, percent of total. The more of these you select, the bigger information in a cell. So let me just add these two and you see what it looks like. This is not going to quite look like what I have in my note, but that's okay. The other 3 items are in the note. So let me hit OK. And there you go. See, our table is getting bigger. And each cell, there's more information in each cell now. See? So how do you read, for example, in this cell? Observed 25. You would expect 31. Percent of chi-square 52. These 3 numbers I had it in my note. Now I added percent row, percent of column. So there you go. These 2 totals add to 100%. So what do these tell me? That means 92% of those who use cell phones, see, use cell phone, percentage of row, 92.3% did not have accident, 7.7% had accident. These are cell phone users who had accident. There you go. Those who didn't use cell phone, 11.1% had accident. So if you compare this one and this total, and let me highlight them. There you go. Look at those 2 totals or percentages. Actually, the greater percentage of those who didn't use cell phone had accident. Okay, now for those who had accidents, the column total. For those who had accidents, 33% were cell phone users, right? Cell phone and had accident, 33%. For those who had accidents, 67%, they didn't use cell phone and had accidents. You see that? So that's how you interpret these percentages. But again, there's our p-value, and we end up not rejecting this null hypothesis. Okay, so let me go back to my note. And there we go. So we covered the example of cell phone usages. And let me see here. Yeah, don't worry about this one. We just did this one. Let me, in fact, delete it. Okay, because I had duplicated it. So hopefully you followed everything we did. It's a pretty simple but very powerful again method for testing hypothesis for nominal data, the ChiSquare test for independence. Very common and very powerful. So with that, we are done with chapter 15. Hopefully you'll be able to do your homework in this chapter, and please watch the video again in case you need to reinforce some ideas. Oh, one thing I want to do real quick, these assumptions. Well, we assume everything we did involves simple random sample, but at most 20% of expected frequencies are less than 5, and cell frequencies or expected frequencies are 1 or greater. Now this means you're not going to have empty cells, right? Because what's lower than 1? 0, right? So this says you got to have at least 1 expected frequency, and that was the case in every cell. And now cells that have less than 5 expected frequencies, let's see if we had any. Here's expected 56, 46, 39. None of them are 5. No. And this one 43, 36, 30. See, none of these expected frequencies are less than 5. So this assumption is met. Looking at our second example, expected frequencies 31, 293, 406 to 43, and 70, and that's it. Yeah, those 4. So no, again, we didn't have any cell frequencies with expected frequencies less than 5. Now if we did have a few that were less than 5, you would count 20%. If this 20% of total cells, then the chi-square is invalid, and that means you just have to find another way to analyze the data. Okay, so with that we are done with this chapter.